I don't know what just happened.
In the quantum fields, aka cosmic strings. They have subatomic thickness but
That was
prodigious
weird.
mass, and they lash through space at close to the speed of light. They could be
Spooky
the
action at
most
a
bizarre
distance, I tell
undiscovered
ya.
entities that probably actually exist. To understand cosmic strings and to convince you that they probably do exist, we need to understand phase transitions in quantum fields. We need to see how a whole universe can freeze like a badly made ice cube. Heat up ice and it melts. Keep heating the water and it vaporizes. More heat still and that water vapor ionizes into plasma. But that's not the final phase transition. Keep heating until you hit temperatures of the extremely early universe, and a phase transition occurs in the quantum fields that underlie all particles. Just as with water, a field's inherent temperature massively changes its
I don't know
behavior.
what is
For
going on
example,
with my
the
stream right
force-carrying
now.
field of the modern universe has a complicated structure. There are many different ways that it can vibrate. These modes manifest as different force-carrying particles moving in what we think of as separate force fields. This gives us our familiar electromagnetic strong and weak nuclear forces. But at very high temperatures, the
Okay,
complexity
so what he was just talking about right here,
of nuclear forces.
um,
This gives us as separate force fields.
so basically, what I've come to understand is that the universe is basically covered in these layered fields. And depending on what these fields are, they can interact with each other in ways that we can't really understand. I mean, we understand, but can't really pinpoint how it's happening. Because at points, it seems like particles are being randomly created and annihilated in an instant in between these fields. But it's based on just the fields interacting with each other. But I watched another video earlier, and it said that basically the universe doesn't even acknowledge that these particles are appearing and disappearing from existence because it happens so quickly. But that makes you think, like,
This
what's the
gives
point of
us
that
our
happening?
familiar
Like,
electromagnetic strong and
why is
weak
that happening?
nuclear forces. But at very high temperatures, the complexities of the quantum fields sort of get ironed out. A little like how the complex crystal structure of ice dissolves when it melts. It seems pretty certain that in the first searing instant after the Big Bang, most of the modes of vibration of the quantum fields vanished. The many force-carrying fields behaved as a single field, generating a single master force. We know for sure that this is true for the electromagnetic and weak nuclear forces. We've re-merged those in our particle colliders. But it's almost certainly the case for the strong nuclear force and the Higgs field also. That's right, I said Higgs field. We think of the Higgs field and the Higgs boson as giving elementary particles their masses, but we should also think of the Higgs as a fifth fundamental force because it arises from the same field structure as the other non-gravity forces. And it's the freezing of this field that can give us our cosmic strings. Now, a quantum field is just some numerical property that the fabric of space can have. The field at any point can oscillate around that value, and those oscillations have quantized energy states. These vibrations can move through space, and we see them as particles. A field's numerical value is called its field strength, and it depends on the amount of energy in the field, sometimes in complex ways. In the absence of particles, a field will always drop to the nearest minimum in energy. This is the vacuum state of the field. In the early universe, the Higgs field had a very simple response to changes in energy, with a single minimum value, and even this vacuum state still contained a lot of energy. The shape of this so-called potential curve depends on the temperature. As the universe expanded and things cooled down, the Higgs field potential developed a bump. The lowest energy value was no longer a single number. Instead, new minima appeared around the old value. Actually, the Higgs field is really characterized by two numbers, a pair of field strengths, and so the new minimum formed a ring around the old minimum, resembling...
I don't like the way that looks.
an item of festive Mexican headwear. So,
Oh.
quite suddenly, the Higgs field everywhere in the universe found itself sitting at a higher energy than it needed. It was momentarily stable at that point, just like a ball sitting at the top of a hill, but the slightest quantum jiggle would send the ball or the Higgs field rolling down in a random direction. And that's what happened. Here and there, across the universe, the Higgs field started falling towards the new vacuum state. We call this vacuum decay. Neighbouring points in a field drag on each other, pulling them towards the same value, just like how the magnetic dipoles in a ferromagnet drag each other into alignment. So, when this vacuum decay started at one point, the neighbouring points would have been dragged to the same part of the Higgs minimum. A bubble of this lower vacuum energy was nucleated, and it expanded at the speed of light. Many bubbles would have started at different places across the universe, and when the bubbles found each other, they merged. The old high-energy vacuum was completely erased.
Oh,
Or
okay.
mostly erased. Just as with ice, topological defects should have formed where these bubbles met. Our ice cube forms sheets, but our Higgs field formed strings. Remember that the vacuum decayed in a random direction towards this circular valley. That means we can ascribe an angle to every point in that space, defining the relative value of the two components of the Higgs field. We'll call that the phase angle. Across a single expanding region of decaying vacuum, the phase angle would have been similar because these points were all pulled in the direction of the initial nucleation event. But independent bubbles may have very different phase angles. When bubbles met, the Higgs phase angle at the boundary tried to rotate to line up. This led to textures of slowly shifting phase angles across the universe. But if multiple bubbles join with different phase angles, then sometimes the lowest energy approach to lining up the phase angles is for them to vary smoothly around a loop, a 2π rotation of phase angle around the intersection. And that left a knot somewhere inside the loop where the fields couldn't align. The Higgs field at the centre of that knot was forced to take on the Higgs value at the top of the old potential hill rather than the valley. It became a fossil of the ancient high-energy vacuum that would persist into the modern universe. This sort of swirly topological defect is called a vortex, and we see 2D versions everywhere, from cyclones to swirls in the hair on your head.
So, basically, when the universe was created, when the universe was created, it wasn't created like together. It was formed in several different parts that eventually joined together as the energy, I guess, expanded. But each individual pocket that formed individually basically had their own energy state or own direction. And so whenever two different pockets emerged, it would create, like a different direction that basically made a smooth transition. So think of a road going straight, and then there's a separate road over here. You would make like a corner, you'd make a corner going over, connecting to it. I guess you can't see my hand over there. But it's possible that with how expansive the universe is, that some of these pockets formed in just the right way, that the energy in a certain point would have never been able to, I guess, fix itself. So it would remain that vacuum, which is these vortexes that they're talking about. So they're basically unclaimed space that has not had a field develop on it because there's no energy. The energy couldn't stabilize on it or something or other. Maybe.
But in a 3D space, like, actual space, this sort of defect manifests as a cylindrical swirl around a central line, and that central line is our cosmic string. Other topological defects may have been possible. For example, a zero-dimensional point-like topological defect would be a magnetic monopole, and we talked about that recently. There are also ways to produce 2D defects called domain walls, but that's for another time. Okay, so we've
What does
managed to
that mean?
freeze the quantum fields amidst the first ballings of the baby universe and woven some cosmic strings. What do they look like and what do they do? Those phase angles really do prefer to line up, which means the loops around the defect tighten as much as they can.
Okay, so he's talking. So this white ball in the center, that is where the vacuum the vacuum energy has just been compressed so much, but I mean, it still can't, be converted into this kind of energy because there's this field going around it that's preventing it from doing that. So this golden orb in the middle is the vacuum, like the pure vacuum before our universe was created, pure nothingness. So a lot of people are theorizing that these are cosmic strings, that if there's multiple of them in the universe, they theoretically should be connecting themselves. So, how in the past people used to theorize that black holes were like wormholes. You could use them as wormholes to go to different points in space, breaking the speed of light. Well, now that's kind of what people are thinking these cosmic strings can do. Um, but once again, I'm sure there's an extreme amount of energy encasing this. I mean, it could be a black hole, maybe. Maybe that's what they're
The
getting at.
filament of
But
high vacuum energy is squeezed down to 1/10 trillionth the width of a proton, and yet it still holds an incredible amount of energy, which gives it the mass of the planet Mars for every 100 meters of length. And
okay,
these
so
things are long. They started as long as light can travel between the nucleation event and the completion of vacuum decay, and then the expanding universe stretched them up to the size of the observable universe. We actually expect multiple nucleation events in each causal horizon, potentially leading to dozens of cosmic strings in a network across the universe. Unlike the topological defects in ice, cosmic strings move and vibrate. They are also under some pretty insane tension, so vibrations travel along them at near the speed of light.
okay,
This
so they're not
inevitably
faster than
leads
the speed
to
of light.
collisions between segments of strings, either two distinct strings or two sections of the same string. When this happens, either the two segments pass straight through each other, or they switch partners, they intercommute. If a straight string collides with itself, it can cut out a loop. Then, if the loop intersects with itself again, it forms two smaller loops, chopping up into smaller and smaller pieces. But also, larger and larger loops keep forming from the original giant cosmic strings. Over time, the size of the largest loops increases, while at the same time populating the universe with their chopped up offspring. Once this intercommutation occurs, a pair of kinks is formed in each of the newly formed strings,
Kinks?
and they speed away from each other along the string
Meow.
at near the speed of light. They're whipped back and forth by the oscillating string, and the incredible mass in these kinks causes them to radiate gravitational waves. In this way, cosmic strings shed energy, and so they slowly decay away. Eventually they vanish as the Higgs field smooths itself out across the filament.
Okay, so
The
I might have
smaller
had
the
it
loops-
backwards. Rather than them being an emptiness vacuum, they may just be extremely high energy where the fields overlapped. That's kind of what it looked like in the video rather than it being the pure vacuum. It looked like it was the overlapping of the fields. So extreme energy. Whoa. Play, please.
size, the quicker they evaporate. So the breaking up of loops accelerates their demise. Okay, so that's what cosmic strings do. Now, how do we find them, assuming that they exist? Well, let's start with these gravitational waves. That radiation should be emitted in beams in the direction of oscillation of the string, so we might see flashes as these beams pass over our gravitational wave observatories. These are likely too weak to be seen at the current detectors such as LIGO, but future detectors such as LISA may be
Holy
sensitive
cow.
enough. Then there's the pulsar timing array. As we've described previously,
We
it
watched this
detects
video.
gravitational waves by looking for irregularities in the period of the fantastically regular flashes of light from pulsars. It also has the potential to spot the telltale signals from gravitationally radiating kinks in cosmic strings. The other way to spot cosmic strings also relies on a gravitational effect, gravitational lensing, which is the warping of background light sources due to the space-time warping effect of gravity. When a massive object sits between us and a distant light source, it bends all passing rays of light inwards, so focusing them towards us. We can see multiple images or even a ring surrounding that lens. A cosmic string would also deflect light towards itself, but that can only lead to a pair of split images, and that could potentially leave a chain of split images across the sky. No such chain has yet been detected, but upcoming gigantic all-sky surveys may give us the data that we need to find these.
I don't even know what that
if we do
means.
find a cosmic string, there's one other point of confusion that we need to settle. Is this a cosmic string, or is it a cosmic superstring? You've probably heard of string theory. We've certainly talked about it enough on this show. It's perhaps the most established candidate for a theory of everything, a theory that brings together all physics as we know it. The fundamental building blocks of string theory are these subatomic one-dimensional filaments called, fittingly,
Tag yourself,
strings.
I'm the blue one.
The strings of string theory have nothing to do with the cosmic strings that I described. For one thing, they're ridiculously tiny instead of universe-sized. However, the universe may have found a way to confuse the two. Many physicists think that in the extremely early universe, the so-called inflationary epoch expanded the subatomic into the cosmic. Some of these string-theoretic strings may have been stretched to universe size by that event. Now those are called cosmic superstrings, and annoyingly they behave like regular cosmic strings in many ways, like the gravitational waves and the lensing, but there are differences. While cosmic strings almost always intercommute when they collide, cosmic superstrings are far more likely to pass straight through each other, which reduces the rate of chopping up into loops. They can also form junctions, specifically where two different types of superstring meet and combine to form a third connected string, which is in a sense a combination of the two. Now, this gives us a potential way to distinguish our cosmic string type. If one of these superstring junctions does any gravitational lensing, it should produce a 6-part image, perhaps with a parade of split pairs approaching
Oh,
it.
whoa.
Observation of such a junction would be the best, dare I say the only evidence to date in support of string theory. We should also expect cosmic superstrings to decay less quickly because they don't chop into loops as fast. That means they should result in a stronger gravitational wave background and possibly a distinct gravitational
That would be
wave
crazy.
signature. Now, we haven't actually found cosmic strings or superstrings yet, but our searches have given us bounds on the range of allowed tensions and therefore energies of these things. And we have to keep looking, because it's very possible that the universe is riddled with veins of its primordial vacuum. If we can find one, who knows what we'll learn. We may discover
in Genshin,
truths
this reminds
about
me of the
the
place
origins of the
on-
universe, or the nature of quantum fields, or the validity of string theory. Many murky mysteries may become as
I don't know what
clear
island it was,
as
but
a
it was the island
well-made
where
ice cube.
they sacrificed the boy.
I mean, what better way to see the inner workings of the universe than to find a crack in the fabric of space-time?
Well, that was interesting. I've never heard of cosmic strings before. That's kind of cool. What'd you guys think about it? Was that cool? No? Alvin, are you there? Alvin! What are people saying in the comments? These people are crazy. That was informative though. That was cool. That was a good. I mean, I thought it was shorter than 15 minutes. I'm gonna be honest. Okay, but I want to go back to. I want to go back to gravitational. What is it? LIGO. Gravitational waves. I don't want to do an old video because there's been new stuff come out since then. I actually think gravitational waves were discovered already. Maybe? Maybe not. Maybe I'm thinking about this stuff. I would actually like to know how LIGO works. That'd be kind of cool to figure out. Or here, we'll watch one on Ice Cube. I'm kind of surprised there's not more. What the hell is this? I'm pretty sure we were watching those videos yesterday. Oh, were those the alien? Those were the alien videos we were watching. Um, let's watch this one.
Here I am at the Ice Cube laboratory, which is part of the larger Ice Cube neutrino detector, which is the biggest, most expensive experiment here at the South Pole and one of the largest in the world.
If you're thinking that there is no way this little building could be a world-class physics experiment, I wouldn't blame you. But looks are deceiving. The real magic of Ice Cube isn't in this building. It's deep in the ice of Antarctica.
I can't believe my stream ended earlier. That was kind of annoying.
Here, deep in the ice below the South Pole Station, you'll find the workhorse of the Ice Cube Observatory, the Digital Optical Module, or DOM. The DOM is an advanced sensor designed to detect effects of neutrinos in the ice. The DOM is constructed of many different parts. There's the glass pressure sphere that protects the DOM from the crushing pressure of the ice, and the pressure band that holds the two halves of the sphere together. There's the photomultiplier, which is basically a light sensor that is really sensitive, which is important for detecting neutrinos. Then there's what's called the mu metal cage, which helps cut down interference with the sensor. There's the main circuit board, and then there's the flasher board, which has light on it so that DOMs can signal each other within the ice and help calibrate the experiment. This function is pretty important because there are over 5,000 of these DOMs deep within the ice that all need to be coordinated and calibrated. All the DOMs are strung together on a cable, and the first DOM is at a depth of 1,450 meters, or nearly a mile deep.
Jeez.
The deepest one is at 2,450 meters, or 1.5 miles deep.
Jeez.
Each string of DOMs is taller than the Burj Khalifa, and the entire array encompasses about a cubic kilometer of ice, hence the name Ice Cube. Okay, so what are neutrinos, where do they come from, and how does Ice Cube detect them? To put it in very simple terms, a neutrino is a fundamental physical particle, like an electron or a photon. It travels very fast, at nearly the speed of light, and it almost never interacts with normal matter. The vast majority of the time, neutrinos just pass right through matter without leaving a trace. In fact, right now there are trillions of neutrinos passing through your body every second, but you can't feel them.
Yes,
This last quality is what makes neutrinos so difficult to study. If a particle almost never interacts with matter, then you need a very large amount of matter to give you the best chance of detecting it. Also, on the rare occasion that a neutrino does interact with matter, the reaction produces light. So you need the matter in your detector to be very clear, because if you can't see the light, you can't detect the neutrino. That's why Ice Cube is designed the way it is. Thousands of detectors in a large amount of very clear ice in a dark place. So where do neutrinos come from? They can come from a number of sources, like the sun and nuclear reactors, but what Ice Cube is looking for is something special. It's looking for high-energy neutrinos that come from outside our solar system, and I'm going to tell you the story of one that turned out to be kind of important for astronomy.
Okay,
like so many great stories, we have to start a long time ago in a galaxy far away. But not this galaxy, this one's too nice. I'm looking for a fuzzier one. Here we go. This is the galaxy TXS 0506, and although you've probably never heard of it, it holds one of the most powerful objects in the universe, a blazar. Blazars are basically supermassive black holes that gobble up matter around them, and in turn start spewing out high-energy particles, like neutrinos, in powerful jets. So this blazar TXS 0506 gobbles up a star or something and spews out all these high-energy neutrinos. Now, the unique thing about blazars, compared to other supermassive black holes, is that their jet of particles is pointed right at our solar system. So our neutrino speeds off from the blazar and heads toward Earth at almost the speed of light, but even so, it still takes a few billion years to get here. Finally, in September 2017, the neutrino passes through the Earth and into the ice of IceCube's detector field, and, lucky for us, it decides to smash into a hydrogen atom there, resulting in a shower of light within the ice. Within seconds, the IceCube computers were able to create a model of its path through the ice and get an idea of where it came from.
Oh, that's cool.
This triggered an automatic alert sent out to telescopes around the world to look at that area of the sky, and when they did, they saw a burst of radiation from the blazar, which basically confirmed that that's where the neutrino came from. This whole event was important for two reasons. For one, it was the first time scientists could say with some confidence that we had found the birthplace of a high-energy neutrino. And two, it was one of the earliest demonstrations of what's called multi-messenger astronomy, which just means taking two very different experiments, like a neutrino detector and a conventional telescope, and using them together to study the stars. But let's get back to the laboratory. Because there are over 5,000 optical sensors running 24/7, IceCube is constantly generating a massive amount of data, and that data needs to be processed and refined before being sent back to the primary host of the project, the University of Wisconsin. That refinement process is the main function of the building, which is called the IceCube Laboratory.
Oh, I saw, yeah, they did have a video on it. I didn't realize it was there.
So when you first walk into the IceCube Laboratory, it actually looks kind of unassuming, despite it being one of the biggest physics experiments in the world. This first room is just a workshop for building maintenance, etc. But through here is where we have the electronics workshop, where the scientists can do small repairs to the electronics if they need to. And then here we have an example of one of the many, many sensors that are down in the ice. All the data they're collecting goes upward through this cable and upstairs to the server room, which I'll show you right now.
You might have seen the snacks I was standing next to, and those are there because you never know when you're going to get hit with bad weather. There's also a bed in the building for the same reason.
Alright, so I've come up to the server anteroom, which has all the readouts of all the data that are coming in. Also all the sensors that monitor the temperature in the server room. And then this screen right here tells them the status of all the sensors in the ice. And then through here is the server room, but first I gotta get an anti-static jacket on. Okay, so this is the server room. This is probably one of the biggest power draws on station because all these computers are going all the time, getting all the data up from the sensors, filtering it, refining it. As you can see, tons of server racks here. This whole entire row going all the way down is just all servers. And if you look above me, there's actually these giant cables coming in from each side of the building. And these are cables coming in from the sensors, feeding all that data upwards. So if you can see how big and thick these cables are, there's 2 layers of them, and they're coming in from 2 different sides. So a ton of data. The first time I walked through here, I was just overwhelmed by the just terabytes of data that are just flowing around me all the time.
A couple other unique things about the IceCube server room. It's actually the only actively cooled room on the entire South Pole Station complex. Every other room is actively heated. It also uses an FE13 fire suppression system to protect the electronics, so if you hear the alarms go off, it's probably smart to leave as quickly as possible. Besides being a world-class experiment, IceCube is also one of the furthest buildings away from the main elevated station, so it's nice to go up on the roof on a nice sunny day and take in the views of the plateau. That's all for IceCube. Remember to like and subscribe if you want to see me make more of these videos, and...
Okay, that was a little interesting, I guess. Let's do the one actually by.
Hi, I'm John Harden.
I'm Yuya.
And we are IceCube's winner uppers. We've been living and working at the South Pole for the last 11 months to take care of Ice Cube and make sure it stays up and running.
Hello, and welcome to the South Pole. What you're seeing here are the colors of our stunning sunrise, which happens just once per year.
Jump scare.
We're sorry we can't be with you live today, but due to how the satellite works, it is actually very difficult to stream consistently. In this shot, we've gone a little bit back in time. In the foreground, you can see the flags of the signatories to the Antarctic Treaty flapping in the wind, surrounding the ceremonial South Pole.
That U.S. flag is torn. They need to change that. That would not pass U.S.
Even
code.
further back, you can see the moon, which looks a little bit yellow because the shot is so exposed, but it is the moon, I promise. You see here an aerial view of the station and surrounding area. The upper left is Ice Cube. To the right are our CMB telescopes, and there's the Dark Sector Road leading out there, which crosses the skiway. Skiway is where the planes land. The station proper is at the end of that road. It's the E with 4 legs coming off of it. 3 of those legs are used for sleeping and berthing, one of which is the gym, and the long side of the E is where general station activities
What did he just say,
take place.
sleeping and berthing?
Sleeping and berthing. 3 of those legs are used for sleeping and berthing, one of which is the gym, and the long side of the E is where general station activities take place. Off to the right, out of frame, is our clean air sector, and near the front of the frame is the backyard, as we call it, which we use for logistics, storage, whatever you can think of. It's the biggest freezer in the world. We're going to get to see a little bit of the inside of the station now.
My squeaky ass
What you're seeing here is
chair.
the galley, which is sort of a central gathering point for all kinds of people. And what you're seeing right now is actually Yuya and I getting ready to talk some stuff over and prep for our trip out to the ICL. The galley is actually a wonderful place. The staff there serves us delicious food of huge variety, and there's always something to do and somebody to talk to there. In the summer, there are more than 150 people on station sometimes. In the winter, there are just 42.
Gotta get
But
water.
the galley always comes through and everybody gets a meal. And indeed, we even do special events for holidays and other things. It's actually really nice when you're down here and you're missing your family. Oh, and there are always cookies available, whenever you want.
Ooh, cookies.
Which can be unfortunate. Sometimes they're a little bit too available. The galley is ringed by windows, as you can see here. And anytime there's even a little bit of light outside, we have the covers off, and we can actually see the sun moving horizontally. It would move from the right to the left in this frame. When there isn't any light outside, we have Aurora cameras up top of the station, and so we can't have any light spilling out onto the snow and interfering with that experiment. So we actually cover the windows.
Birthing.
Other things
I
in
think
the galley include this main
laying
table where
about,
we sit,
not like
and in the
giving
back
birth.
you
I
can
thought
see
he
the
was
galley
talking about giving
scroll, which
birth.
tells us important things about the station. Right now it's telling us that the internet isn't currently
ASMR
up, but will be
stream.
soon. And it can also tell us things like the temperature. And as you may have heard, it can get somewhat cold at the South Pole.
Okay. I got Aldi's the other day. And I got just like a chip variety thing. They're called Clancy's. I opened the bag upside down accidentally. But they're called Clancy's. They're the worst chips I've ever had. The potato chips are fine. But like their Doritos, not good.
We've decided what we want to do, and now it's time for us to gear up and get ready to head out for the day. To do that, we put on our ECW, or Extreme Cold Weather gear. You can see we've already started with the iconic Big Reds, and we're putting on our balaclavas and hats and gloves and boots in order to minimize the risk of cold injury. The temperatures you saw there are no joke. You can get frostnip on exposed skin in less than 5 minutes. So we have to make sure everything is covered, and it's covered and well insulated. One of the main reasons we go
All the
out
chips
and
are, like,
brave the
broken,
cold
too.
here at the South Pole is to support our science, which goes on at our outbuildings. The science is divided into several sectors, first of which is the clean air sector. We also have the quiet sector and the dark sector. The clean air sector is used by NOAA, and it is upwind of our power plant. It has some of the cleanest and most well-mixed air on the continent and even the world. They can measure all sorts of contaminants, and they can even measure CO2 levels on the regular going back decades. The quiet sector minimizes vibrations, used to monitor seismic activity, and the dark sector includes IceCube and the Cosmic Microwave Background Telescopes, and we try to minimize radio wave interference. So let's head out and take a look at the dark sector. As we exit the station, we come through the so-called Hercules door. All exits to the station use this heavily insulated door so that we're not wasting heat. We have a finite amount of
Tonkatsu,
fuel
potato
here at
chips.
the South Pole, and we don't want to waste it. All of our electricity and heat down here comes from burning the jet fuel that we get called AN8. We go through several 100,000 gallons a year, most of which is dragged here in bags on what is called the Traverse. The Traverse is a 900-mile tractor pull from McMurdo all the way to South Pole Station.
Ooh. Tractor pull.
As we start our walk to the dark
We
sector,
in the
you will see
country?
two kinds of snow. On the right is what we call groom snow, relatively packed down, nice to walk on. On the left is ungroomed snow, snow that the
They're
wind
grooming
has
their
been
snow?
shaping for quite some time. And what forms in ungroomed snow are called sastrugi. Sastrugi form because the ice crystals that form this top layer we're walking on like to stick to each other, and when they do, they shape the wind that goes around them.
That's cool.
So the interplay between the stickiness and the wind produces these curves and overhangs and nice features which are beautiful to look at and all kinds of fun to trip on when it's dark outside.
Yeah, I would be falling.
As we walk out to the dark sector, we will cross the skiway where the planes land, and when we do, we will be on top of IceCube. To give you a sense of scale of this detector, the ICL over on the left there sits in the middle of it, whereas the Cosmic Microwave Background Telescopes on the right are just about 2/3 of the way to the edge of the detector. All in all, the footprint is around a square kilometer. Now don't worry, we're not going to be hurting anything. There's a mile of ice between us and the top of the sensitive part of the
I'd be jumping
detector.
up and down walking across
Below
that.
that, it extends for another halfway to the ground. And seeing as we're almost 2 miles up here, that's an incredible amount of ice. But up here on top of the ice, as we saw earlier, it can get quite cold. It isn't just the raw temperature making things cold, although, that contributes, but the wind. The wind can really be worse, because what it can do is it can find any crack in your ECW, get in, blow around, and just make stuff cold. Usually it's the cheeks or the bridge of your nose or the brow that this is a problem for, and it's especially a problem when you have to walk directly into it. But it's also a problem because it will pick up the top layer of snow, and it will really reduce the visibility. And when the sun already isn't shining, then this is an extra problem. Now,
Why don't they put like
in this,
lights out
we
there?
have to walk about 2/3 of a
Oh,
mile
you know
from the
what?
station to the ICL, and this
Never
can take
mind.
anywhere from 10 minutes on groomed snow on a
Probably
bright summer day
interference.
to 20 to 25 if it's bad visibility and we're climbing over sastrugi in the dark winter. Typically, we have to do this 2 to 3 times a week for general maintenance, but sometimes we have to walk out on incredibly short notice or even in the middle of the night if something went wrong at the ICL and it needs to be fixed immediately. Usually, we're just bringing ourselves out
Could you
there.
imagine having to
although
walk
also
out there
our cameras,
alone?
typically. But occasionally, we have to bring a piece of hardware to or from
That would be
for
absolutely
debugging
terrifying.
or other sorts of fixing. If we have to do anything more substantial than that, which is pretty rare, we would like to use a vehicle, because if you have to carry anything heavy outside, you end up compressing your glove, which gets rid of the outer layer of insulation of air, which is a recipe to get cold fingers very, very quickly.
I would be falling.
Here we are in the bottom of the ICL, where we maintain an electronics lab. Spares are limited here at the South Pole, especially during the winter, so we have to be able to repair whatever we can. I'm sitting over there on the right, repairing a card that allows us to talk to the DOMs, whereas Yuya is over there on the left, repairing the power supplies to the DOM hubs, which are the computers that allow us to integrate all of the data from the DOMs. What we see here is the DOM itself. To give you some idea of it, it's about 1.5 feet in diameter. The entire
able to
lower
just,
half
like,
is
Take
used
them out of the ground
just
and
to
replace
collect
them if they
light.
need to.
The upper half has some sensitive electronics that we use to both power the pixel and to determine if it's seen any light whatsoever. The cable that you see coming out of there is how it talks to the surface. Let's move upstairs to our control room. We maintain a room with a couple of workstations next to our main server room for when we need to do pure computing-based tasks, but we don't want to be near the noise of the servers themselves. On the left, you can see Yuya checking in with the terminal application, and we both have our live monitoring of the system up. The live monitoring makes sure nothing goes out of sorts with the network without us knowing about it. And if anything critical happens, it will page us so that we can fix it as soon as
That's
possible.
either where they're at is either the safest place
And
on
here we are
Earth
in the server room, the beating heart of IceCube.
or the least
What you see
safe
behind
place on
those red
Earth.
wires
Because,
there
like,
are
if
the
something
DOM hubs.
happens,
Each of the DOM hubs is
like, their
responsible for
electricity
one
goes
string
out,
of
their
DOMs.
generators go
And
out,
on
like,
each
they're
string of DOMs
fucked.
are 60 DOMs.
I mean, I'm sure
So
they
each
had,
DOM
like,
hub manages
backups
60
and
DOMs.
bunkers and stuff like
The
that, but,
DOMs
like,
communicate with the DOM hubs
what
through
happens if
these
the
red
world goes
wires,
into nuclear war
15 of
and
which
they don't have a way to
are
get back?
used for
Like,
each string. We call
or
them
say
quads
somebody
because
sends
each
a
red
nuke
wire
over to
manages the
them. Who's
information
going
of
to
4
stop
DOMs.
that?
All of those DOMs
There's
go into the
probably
DOM
not
hubs,
nuclear
which
defense
are all
on
networked together.
Antarctica.
And importantly, they're all networked to our processing farm. And the processing farm is very important because it allows us to determine from moment to moment if anything interesting has happened. Now,
I'll be right back.
if you're an IceCuber,
Bathroom break.
the word interesting means if we've seen an astronomical neutrino, typically. We see about one of those per month. And when we do see them, our processing farm not only lets us know that they've happened, they let us know what energy they happened at and which direction they came from, down to about a degree. And then we can email the north, and if anybody with other kinds of telescopes want to follow up on it, they can do that. Now, this brings us to the other important feature of IceCube. It's our uptime. We're more than 99% up, and we're actually a good deal more than that most of the time. It's why Yuya and I have to be on the ball and on call as much as we can to fix it if anything ever goes down. Being up this often allows us to guarantee that we will see whatever happens in space, at least as long as it happens in neutrinos. And one of the most interesting things that can happen in neutrinos is a supernova. And what's especially interesting about that is that we think that the neutrinos from a supernova will come out 15 minutes to an hour before the light of the supernova, which means that with IceCube, we can alert everybody else on the planet that a supernova is about to happen with a good at least 15-minute lead time. And being able to see a supernova with modern technology would just be an incredible scientific advance for us. Although we only see about one of those a century, so we're crossing our fingers down here. Well, that about wraps it up for today, but we wanted to thank you all for being here with us. Yuya and I are going to be here on this snowdrift enjoying the sunrise, but we honestly couldn't leave you without sharing some of the nighttime images that you can see down here. It's a little hard to film properly outside, but you can do a nice time lapse, and honestly, the eye can see these things pretty well as well. The Milky Way viewing and the aurora viewing are just spectacular. The first time we saw auroras, just after sunset, I called Yuya out onto the roof and we just spent some time staring at them.
Did we learn anything while I was gone? Yes, I know you want to go on that. That's why I got it out. Damn, I missed it all, didn't I? Oh well. That's okay. Well, we still have 2 hours. What are we gonna do for 2 hours? Oh, I didn't plan this very well. What else? You know, I kind of been wanting to go back and play Hades. I kind of want to do Hades. Maybe I'll do Hades. I think I'm going to play Hades. We'll put on another video about gravitational waves. Let me change it. Oh, it's running. Game capture properties. Not Zagreus' head being cut off. What the hell is PBS posted about now?
Thank you to Ren.
Okay, your music is kind of loud. I do like your music though. It's really good. What's this? No.
For supporting PBS.
That's still kind of loud.
In the world of quantum mechanics, it's no big deal for particles to be in multiple different states at the same time, or to teleport between locations, or to influence each other faster than light. But somehow, none of this strangeness makes its way to the familiar scale of human beings, even though our world is entirely made of quantum weird building blocks. The explanations of this transition range from the mystical influence of the
What?
conscious mind to the grandiose proposition
Y'all.
of multiple realities. But there is one
like-
explanation that feels as down to earth as the classical world that we are trying to explain.
That was weird.
Let's see if it actually makes sense.
There was like a border. There was like a wall that my mouse wasn't allowed to pass through. That was strange.
In quantum mechanics, particles don't have definite properties. Rather, they're described by something called the wave function. In fact, a particle is its wave function, a fuzzy distribution of possible properties that only become sharply defined in particular circumstances. For example, when we make a measurement of a particle, the property that we're measuring seems to be plucked from the wide range of possible values defined by the wave function. We say that the wave function collapses. It appears to shrink to a window whose narrow width is defined by the precision of our measurement. A famous example of this is Schrödinger's cat. A scientist puts a cute kitty in a closed box with a radioactive atom attached to a vial of poison gas. The atom has a 50-50 chance of decaying, triggering the release of the gas and so killing the cat. Prior to opening the box, from the scientist's perspective, the atom's wave function exists in what we call a superposition of states. It is simultaneously in a
states at
state of
once.
decayed and not decayed. So then, is the cat also in a superposition of dead and alive? Honestly, probably not. At some point between atom and cat, the fuzziness of the atom's wave function collapses into one of the two states, and becomes or. Decayed and not decayed becomes decayed or not decayed. And the cat is alive or dead, not alive and dead. The quantum becomes classical at some point between the subatomic
What?
and the macroscopic.
What?
Wave function
What?
collapses in a
What
state
did
of
he just
decayed
say?
and not decayed. So then, is the cat also in a superposition of dead and alive? Honestly, probably not. At some point between atom and cat, the fuzziness of the atom's wave function collapses into one of the two states, and becomes or. Decayed and not decayed becomes decayed or not decayed. And the cat is alive or dead, not alive and dead. The quantum becomes classical at some point between the subatomic and the macroscopic. The idea of wave function collapse was first proposed by Werner Heisenberg, one of the
I
principal
hate that.
founders
I
of quantum
hate
theory.
that. I had such a hard time with
Heisenberg
that.
and his friend Niels Bohr were convinced that this wave function collapse was real. It's a central part of their Copenhagen interpretation of quantum mechanics. But neither physicist claimed to know where or how wave function collapse actually happened. And fair enough, because it's confusing. Quantum superpositions can involve many quantum particles. So how far can the superposition extend? The atom, the radioactive detector, the vial of poison, the cat, the scientist?
All of it.
Opinions on the matter span all extremes. John von Neumann and Eugene Wigner thought that wave function collapse happened at the instant of subjective awareness. In other words, they thought that consciousness collapses the wave function. At the opposite end of the spectrum, many physicists believe that the collapse of the wave function is a fiction. For example, in Hugh Everett's many worlds interpretation, the wave function never collapses, rather it lasts forever, splitting into parallel realities. And we have the idea of quantum
What the fuck does that
decoherence, where
mean?
different parts of the wave
They're going to
function
split into different
simply become
realities. It would
unable to
exist in one
interact with
reality and
each
then
other.
it not exist in another
And we
reality.
also have de Broglie-Bohm pilot wave theory, where particles already have defined properties that are hidden within the wave function. The wave function may collapse, but particles maintain a rigid physical nature. We've discussed all of these ideas in the past, but today we're going to look at a different approach to collapsing the wave function. One that accepts the wave function as the fundamental building block of reality, unlike pilot wave theory, and one that avoids multiple universes by insisting that the collapse really does happen, but it also avoids mystical seeming explanations like consciousness-induced collapse. Our story starts in 1986, when three Italian physicists, Giancarlo Gerardi, Alberto Rimini, and Tullio Weber, published a paper that outlined what was to become known as GRW theory, the first in a new class of alternate quantum theories called objective collapse theories. In objective collapse theories, wave functions are real physical entities that literally collapse when they're measured. But the collapse has nothing to do with a conscious observer or any subjective explanation. The wave function and the collapse are completely real, completely objective, hence the name. To understand how objective collapse theories work, we just need a little more quantum mechanics. The behavior of the wave function is described by the Schrödinger equation, which tracks the wave function's evolution through space and over time. As we've discussed previously, the Schrödinger equation is a linear equation, which just means that if you add together solutions to the Schrödinger equation, the result is also a solution to the equation. This is part of what makes superposition possible. It allows different parts of the wave function corresponding to different possible measurement results to evolve independently of each other. The other thing about the Schrödinger equation is that it's time reversal symmetric. Running it forwards generates future states, but running it backwards lets you perfectly recover the past states.
Oh.
When wave function collapse happens, different parts of the wave function interact with each other instantaneously and non-locally and non-reversibly. This means that wave function collapse is a non-linear process and it's non-reversible. It's not part of the math of the Schrödinger equation. So to model the effect of wave function collapse, Gerardi, Rimini, and Weber added a non-linear term to the Schrödinger equation that could cause this wave function collapse in just the right way to explain why subatomic systems...
Sorry. I'm just on YouTube. I am looking up gravitational waves. So I'm watching this stuff because there's going to be two big announcements. But this is on PBS Spacetime. And they have a lot of good videos, it seems like. And then... Oh, God, I don't know.
Have you ever asked, what is beyond the edge of the universe? And have you ever been told, thank you to...
One second. There you go. There's the, that's their YouTube channel. No probs, no probs.
to Ren for supporting PBS. In the world of quantum mechanics, it's no big deal for particles to be in multiple different states at the
No
same
worries,
time,
don't worry about
or
it.
to teleport between
Happy to
locations,
help.
or to influence each other faster than light. But somehow, none of this strangeness makes its way to the consciousness-induced collapse. Our story starts in 1986, when three Italian physicists,
We already saw that.
as we discussed different possible math, of the Schrödinger equation. So to model the effect of wave function collapse, Girardi,
Here we go. We're
Rimini,
right
and
here.
Weber added a nonlinear term to the Schrödinger equation
I love
that could
Hades.
cause
Hades
this
is
wave
so much
function
fun.
collapse in just the right way
can't
to
wait for the
explain
second one to
why
come out.
subatomic systems could be quantum, but large systems were always classical. Think of this nonlinear action as a rare and random hit that the wave function takes at a particular location. That hit causes it to collapse to a particular value, and when it collapses, it immediately collapses all parts of the wave function that it's connected to. The key to making this work is that these hits are very rare. It's incredibly unlikely that a single
I don't
isolated
understand
quantum
that.
particle will undergo
I'm gonna be
collapse
honest.
during the course of an experiment. But the more particles you
shit.
add, the more likely that one of them experiences collapse, and that single event collapses the wave function of the entire system. Any attempt to measure an isolated quantum system necessarily means bringing lots of particles into the picture, in the measurement device and in your own brain. With enough particles, collapse becomes inevitable. So this hitting mechanism gives a potential explanation for the quantum classical divide. It simply depends on the number of particles involved. Small things can stay quantum, but the chance of collapse to classicality increases with size, and big things are essentially never quantum. GRW suggested that the collapse rate should be at about 10 to the power of minus 16 hits per second per particle. With this value, a single particle wave function remains uncollapsed for around 100 million years. But if you have Avogadro's number of particles,
I was about to fucking say
6 by 10
Avogadro's
to the
number.
power of 23-ish particles of a macroscopic object, you expect a collapse every 10 nanoseconds or so. GRW is a revolutionary theory
Okay, so
that
it's-
inspired many subsequent models, like continuous
It's consistent.
spontaneous localization. In CSL, physicists imagined that the localizing mechanism was a randomly jiggling field.
I have. This is my
like
second
the frenetic
playthrough.
Brownian motion of pollen grains floating on
But it's
water.
been a long time. It's
Matter's
been like
interaction with this fluctuating
4 or
field
5 years
will
since I've played
continuously
Hades,
collapse
I'd
the wave
say.
function, in contrast to the discrete and violent hits of
Oh,
GRW
shit, I didn't mean to
theory.
land on the trap.
But neither of these models really tried to explain what the
I'm
mechanism
so excited for the
actually
second one.
was. They just thought there was some mysterious field that interacted
I didn't like
with all
100%
matter,
complete it, but I did
almost
complete
like
the
it was a
story.
fifth fundamental force.
And I think I unlocked all the
But Lajos
weapons.
Diyoshi
But
and
maybe
later
not all the, like, the
Roger
upgrades to
Penrose
them.
saw no need for some new fundamental force. They thought nature already gave us a perfectly good source of wave function collapse. Gravity, gravitational decoherence, would simultaneously explain two mysteries of physics: what causes the transition from quantum to classical, and why can't gravity be quantized like the other forces? All the collapse models attempted to answer point 1, but only Diyoshi and Penrose's model could answer 2. Gravity can't be quantized because gravity isn't quantum. They proposed that gravity and the three other quantum forces are diametrically opposed. Quantum mechanics rules when things are small, but at enough mass, and the gravity of the system will cause it to rapidly decohere into a classical object. Instead of gravity being quantized, Penrose's theory predicts that quantum mechanics will be gravitized. For example, consider a massive object. General relativity says that the mass from the object will warp space-time around it, but quantum mechanics says that this object can be in a superposition of two locations, where it is both here and there at the same time.
Here and there.
Put these two facts together, and you'll get a superposition of two different geometries of space-time. According to Penrose, this isn't possible. The instability introduces a nonlinear term in the Schrödinger equation, causing the wave function to rapidly and randomly choose to make the object appear either here or there, but not both. Because each of these objective collapse models involves modifications to the Schrödinger equation, they are not mere interpretations of quantum mechanics, they are distinct theories with unique predictions. This means that, unlike other interpretations that we've discussed, for example Bohmian mechanics or many worlds, objective collapse models can actually be tested. Some tests have already ruled out some of the models and placed restrictions on the nonlinear parameters of others. Direct tests of collapse models would involve putting a macroscopic object in a superposition of being here and there, then measuring how long it takes for the superposition to collapse. This time should be proportional to the size of the object. Experiments are approaching the masses necessary to make such direct measurements, but they're not quite there yet. Instead, physicists have come up with clever ways to look for other indirect signs of collapse models. For example, the models imply that a quantum wave function will be randomly tossed about, jostled by gravity or some other collapsing field. If the quantum object happens to be electrically charged, then the constant jiggling and acceleration caused by this Brownian motion means that it will emit radiation. Last year, scientists working in Trieste, Italy, tried to measure this radiation
I would
effect.
get it if it's
They put an
cheap.
8
If
by
it's
8
expensive, I
centimeter
would not get
germanium
it. Because the new
crystal
game
in
will
a
come out,
cryostat
and that one will
carefully
probably be
measured the
better to
amount
play
of
anyways.
radiation emitted. The
But like, if
predicted
you
effect
can
was
get it
so
on a discount,
tiny
I think it would be a
that the
good
researchers had to go underground to try to minimize as many background
I think
sources
I
as
paid.
possible. In the Gran Sasso
I don't think I paid
laboratory,
full price for it
a main
whenever I
source
got
of
it,
noise,
'cause I got it a
cosmic
little bit after
muons,
it was already
was reduced by a
released.
factor of nearly 1 million. Then they further shielded the crystal with layers of copper and lead. With such pristine conditions for a high precision measurement, the scientists in Trieste were able to measure single photons emitted from the germanium crystal. After watching the crystal for 2 months, they had detected a grand total of 576 photons. Now, this isn't enough to confirm or refute the general idea, but the scientists were able to place tight restrictions on the value of the free parameters in the Dioschi-Penrose model.
I don't know what this experiment was
It even
for.
ruled out Penrose's original version of this model. There are still
I don't
many
know what he's talking
candidates
about.
for objective collapse models that have not been ruled out by experiments, so stand by for a jubilant confirmation or for a sheepish never mind. Whatever the case, it's exciting that there are real and accessible experimental paths to investigating one of the biggest unanswered questions in physics, and one which we'll be coming back to. What, in fact, is the quantum wave function?
What is it?
And how does this abstract system of shifting realities give rise to our solid, familiar, and singular spacetime? Thank you to Ren for supporting PBS.
Oh,
Ren is a website where you calculate your carbon footprint.
we still have more.
couldn't do this without you. Today, though, we're going to give a extra special phantom. And who put my cat in that funny box, and why isn't he purring anymore? The direction of making more space-time. Last time we tackled a question of utmost gravity. Literally, how does gravity itself escape the inescapable gravity of a black hole? The Buzz Ben asks, what happens when gravitational waves pass through black holes? Is there gravitational lensing? Well, that's exactly right. Gravitational waves have to move along the same fabric of space-time as everything else. After all, they are wiggles in that very fabric. So they get deflected by gravitational fields just like anything else. If that gravitational field is made by a black hole, then the result depends on how direct the hit is, and on the relative size of the black hole and the wave. A gravitational wave whose wavelength is short compared to the black hole's event horizon can be completely swallowed, while a larger gravitational wave will get deflected or partially absorbed.
Okay.
The absorbed energy can go
So, I mean,
into changing
a
the black
good
hole's
way to think
velocity,
about
but also can be
gravitational waves
added.
is literally they are waves like in water. They ripple just like water, and if it's a small enough splash, you know, if there's something in the water, it might absorb most of that impact, whereas a bigger one, it may be able to go around it. So that's pretty, I mean,
to the black hole's
straight
mass.
to the point
Buzzben
explanation
also
on that,
asked
I'd
whether it's
say.
possible to focus gravitational waves to a single point to create a black hole without mass. Well, the answer is again yes. Just as it's possible to create a black hole from pure light, a so-called Kugelblitz, if you could focus enough energy from gravitational waves into a small enough region of space, you could actually make a black hole from those waves alone. Ryan
Okay.
R. asks
We're about to go down
how
a
we can know
Kugel
that a black
splits
hole's mass
rabbit hole.
has time to crush down to the singularity, given that time dilation slows the event down during that collapse. So this is a confusing point. The time dilation that we talk about approaching a black hole event horizon is not from the point of view of the falling matter, but from the point of view of a distant observer. Only the distant observer sees matter approach a state of frozen time. And you're right that from that person's point of view, the singularity, in fact the entire event horizon, never quite finishes forming. But from the perspective of the falling matter, it most definitely forms, and it is definitely squished.
Wah.
though whether it's to a singularity or not is still not really known. On that note, Priscilla Ratnayage asks, if an outside observer sees matter slow and freeze at the event horizon, what happens when the event horizon grows? Does that matter get swallowed up?
This bitch about to
This
kill me.
is tricky because the definition of the event horizon is also tricky. In an idealized black hole, the event horizon is defined from the perspective of an observer at infinite distance, aka very, very far away, which is, after all, where you want to be relative to a black hole.
Oh shit, I just died.
The event horizon is that surface around the black hole below which no sublight speed object can escape. And by escape, I mean reach you at your infinite distance. And it's the surface from
Okay,
which
I have
light...
had this burning question. What happens if an object reaches absolute zero? Because in my mind, for some reason, I was just like, oh, it's going to create a black hole. That's what absolute zero is. It gets so cold that no energy can escape from it. And so from that, at that point, it just starts, you know, cold and spreads. So it's just going to spread like a black hole. It's going to get bigger and more dense. But that is not correct. I know that's not correct, but for some reason I feel like that should be correct. Okay, I know we can't, but what happens if we do? I want to know what happens if we do reach absolute zero. Of course. Of course. Listen, PBS Spacetime is actually pretty good. Are they still posting clips?
Have you ever asked, what is beyond...
Oh, they are awesome. Dude, they have some pretty good stuff, I'd say. Dr. Matt O'Dowd. He's pretty dope. I like him.
The mysterious zero-point energy, the quantum vacuum, has been a misrepresented subject of science fiction and pseudoscience baloney for too long. Let's talk about what vacuum energy really can and really can't do.
Okay, so maybe in this video, vacuum energy, we're going to talk about what, you know, the space that existed before the Big Bang. So when there was nothing, essentially.
It seems pretty crazy that space itself might contain a higher density of energy than the nucleus of the atom. This is the prediction of quantum field theory, that there exists an energy of the vacuum resulting from the non-zero zero-point energies of the quantum fields that fill our universe. For the electromagnetic field alone, this energy density has been estimated to be up to a crazily high 10 to the power of 112 ergs per centimeter cubed. On the other hand, our observations of the accelerating expansion of the universe suggest a vacuum energy density of only 10 to the power of minus 8 ergs per centimeter cubed. As we discussed in our episode on the vacuum catastrophe, this mismatch between the measured and theoretical values of vacuum energy is one of the greatest unsolved problems in physics. Despite this minor glitch, quantum field theory is arguably the most successful theory in all of physics in terms of sheer predictive power. This means we should take the idea of zero-point energy seriously and are justifiably perplexed at the mismatch between theory and measurement. But the scientific validity of zero-point energy has also encouraged some pretty terrible pseudoscience and outright quackery on the subject. From accessing this energy as a free power source, to manipulating it to generate warp fields, or pushing against the vacuum energy in propulsionless spaceship engines. Today, I want to debunk some of the nonsense surrounding the quantum vacuum. Let's start with the physics. If the vacuum has an energy density of 10 to the power of ridiculous ergs per centimeter cubed, where is it? Why can't we pull infinite free energy out of nothing? Well, the answer lies in entropy and the second law of thermodynamics. Entropy can be thought of as a measure of the specialness of the arrangement of a system of particles. Higher entropy means a more disordered arrangement. The universe tends towards disorder, and so a highly unusual arrangement will decay over time. The entropy of a closed system always increases, and that's the second law of thermodynamics right there. We harness that decay of order whenever we draw energy from a system. For example, the piston in a car engine only rises when the interior chamber becomes much hotter than the exterior. The combined volume of the inside and outside of the piston chamber is in a low entropy configuration. It's a special, unusual configuration of particles. In its return to high entropy equilibrium, energy is extracted and your car accelerates. But try to drive your car in a dense 1500 Kelvin atmosphere, and that piston has no reason to rise. It's already in equilibrium. Your car doesn't go anywhere, and then it explodes. So even if a system contains a lot of energy, that energy may be inaccessible. And this would be the case even with an extremely energetic quantum vacuum. On its own, the vacuum is the same everywhere. It's already in perfect equilibrium. Energy is extracted in the movement towards equilibrium, in the increase of entropy. No such movement is possible for the vacuum, and so the vacuum contains no useful energy. This is why so-called zero-point energy machines are baloney. They claim to access an inexhaustible source of energy, but no such source exists. In order to access vacuum energy, we'd need to introduce a disequilibrium. In fact,
I missed
we
that
need
whole video. I'm so sorry, y'all.
an episode on the vacuum catastrophe. This mismatch between the measured and theoretical values of vacuum energy is one of the greatest unsolved problems in physics. Despite this minor glitch, quantum field theory is arguably the most successful theory in all of physics in terms of sheer predictive power. This means we should take the idea of zero-point energy seriously, and are justifiably perplexed at the mismatch between theory and measurement. But the scientific validity of zero-point energy has also encouraged some pretty terrible pseudoscience and outright quackery on the subject.
Quackery.
From accessing this energy as a free power source, to manipulating it to generate warp fields, or pushing against the vacuum energy in propulsionless spaceship engines. Today, I want to debunk some of the nonsense surrounding the quantum vacuum. Let's start with the physics. If the vacuum has an energy density of 10 to the power of ridiculous ergs per centimeter cubed, where is it? Why can't we pull infinite free energy out of nothing? Well, the answer lies in entropy and the second law of thermodynamics.
Boo.
Entropy can be thought of as a measure
Fuck
of the
the second law of
specialness of the
thermodynamics.
arrangement of a
If
system
we
of
didn't
particles.
have that, we could have
Higher
clean
entropy
energy,
means a
bitches.
more disordered arrangement. The universe tends towards disorder, and so a highly unusual arrangement will decay over time. The entropy of a closed system always increases, and that's the second law of thermodynamics right there. We harness that decay of order whenever we draw energy from a system. For example, the piston in a car engine only rises when the interior chamber becomes much hotter than the exterior. The combined volume of the inside and outside of the piston chamber is in a low entropy configuration. It's a special, unusual configuration of particles. In its return to high entropy equilibrium, energy is extracted and your car accelerates. But try to drive your car in a dense 1500 Kelvin atmosphere, and that piston has no reason to rise. It's already in equilibrium. Your car doesn't go anywhere, and then it explodes. So
then you
even if
die.
a system contains a lot of energy, that energy may be inaccessible. And this would
So, excuse me. So I don't think I don't know, because there's a couple things that go in my mind whenever I think about the quantum realm. I mean, science has this really eerie way of repeating itself. So like, you see how the universe is formed, like you see how galaxies operate, you see how solar systems operate, and those solar systems, you look down, you look at a cell, you start looking at like atoms and then photons and like all that stuff, and they all like have similar patterns. So it's just very weird at how repeating everything seems to be. So I don't know if you would like actually be able to go down into it, but I mean, it could be the whole Horton Hears a Who situation where you just keep looking in smaller on stuff and you keep finding out, you keep finding smaller things and then you think that's it, but then you can continue to go down further and you find even more smaller things, kind of like um, if there was the whole uh, like multiverse, infinite universes or whatever. I think that's how it would exist, like basically everything collapsing inward on itself. Um, but quantum mechanics, like I know this sounds crazy, but quantum mechanics to me sounds like magic because we don't know how it works. We don't know what goes on, and it can do some really crazy things that don't make sense. Now, I'm sure as time goes on, we'll figure out why these things are working, and it'll make sense at some point, with mathematics and experimentation and stuff like that. But I don't know. The quantum mechanics is super super interesting, and I think it will. Quantum computers are really interesting because they're able to operate much quicker than standard computers for running simulations. Um, and it's basically because they're able to. Standard computers have on off basically one or zero. But quantum computers, they can exist in the on and off state at all times until the measurement is taken. So you're able to get a lot more information, a lot more reliable information from um, simulations with quantum computers because they're able to take in a lot more variables and do much quicker calculations. Um, but I don't know, it's crazy. Yep, yep. And we're that tiny speck on a flower, and then we have flowers, and then there's tiny specks on our flowers. It's kind of crazy to think about, but who knows? We may never know. That's I guess, the
Be the case
mystery
even
of
with an
life.
extremely energetic quantum vacuum. On its own, the vacuum is the same everywhere. It's already in perfect equilibrium. Energy is extracted in the movement towards equilibrium, in the increase of entropy. No such movement is possible for the vacuum, and so the vacuum contains no useful energy. This is why so-called zero-point energy machines are baloney. They claim to access an inexhaustible source of energy, but no such source exists. In order to access vacuum energy, we'd need to introduce a disequilibrium. In fact, we'd need to
Chaos.
reduce the vacuum energy in one region of space. The universe would then try to fill that energy whole, and we could harness that to extract energy. In fact, there's one way to do this, with the Casimir effect.
So it's
If you
basically
bring
like
a pair of
the hydroelectric generators. I think I've seen them where like it looks like a plunger on top of the lake, and it'll push down the water, and it'll like almost cause a void, and then it'll create waves, and then once that water comes back to fill that void after it's been lifted, all that energy is released, so like it explodes up. So I think that's kind of what they're talking about there.
conducting plates very close together, a proportion of the virtual particles will be excluded from between them. By cutting off certain frequency modes between the plates, you lower the vacuum energy in that region. The result is a pressure differential that produces a measurable force, pulling the plates together. Now we talk about that in detail here. So what
They're just
about
basically
building a
removing
Casimir
stuff from
engine?
it.
Unfortunately, no. While that initial pull between the plates may seem like a free lunch,
Definitely.
to extract continuous energy,
Definitely.
you need to pull the plates
Nah, I'd
apart
be chill
again.
about it.
This takes as much energy as you
Because,
originally gained.
as much as I like to think that my ideas are right, I am just talking out my ass. I have no idea what any of this means. I have a very limited amount of information that I'm working with, and biases. I'm gonna explore what sounds the most interesting to me, the most believable to me, or even the most unbelievable to me. Whatever suits my interest at that time. So I like to make sure that people understand that what I'm saying. I mean, I don't know what I'm talking about. I'm just bullshitting. I'm having fun. You know, and please, if I'm ever wrong, correct me. I don't want to be stupid. I want to know that I messed up, you know. Oh, don't worry, don't worry. I mean, honestly, none of this stuff means anything. Because all of this is happening around the world around us, you know, in the universe that we live in. So all of this stuff is going on. We just don't know about it. We're just now able to see this stuff that's going on. But I think quantum mechanics proves that every single thing in this universe is connected in some way. You know, whether it's in the form of wave functions or space-time or um, you know, uh, neutrinos, gravity. I think every single particle has to be connected. Otherwise, I don't think the universe, you know, the space of the universe, our system would exist. I think it all has to be connected in some way. Um, and I think we're just now getting to the point where we're able to see, oh, these particles are more connected to these than we thought, but how are they connected? You know, we're not able to see how they're connected, and that's kind of what freaks us out, is that we're not able to understand what's going on, so it does seem scary. Um, but I think once we start getting further down into quantum mechanics and science and stuff like that, well, I mean, quantum mechanics is science. I think quantum mechanics is going to rule the world. I think that is the most important topic for the longevity of humans, just because with the implications that come with quantum mechanics, we could almost manipulate matter however we needed to. Um, Hell yeah, we're talking shit. Mad shit. I mean, literally, that's kind of what we are. It's, to me, we are, I mean, whether or not we're a simulation, we are a simulation because, I mean, I don't know. I don't know what's after. At least, I don't, I don't think there's anything after that. And if it is, it's not what most people expect it to be. I think everything is energy. You know, everything has energy. And once we die, we just were a part of that background energy. So,
Another popular notion is that the reduction of energy between Casimir plates can be considered negative energy, and so could be useful for all of those
see,
wonderful things that negative energy can do, like opening wormholes or creating an Alcubierre warp field. Well, if we define the average vacuum energy as zero, then the Casimir effect produces negative energy. Unfortunately, the vacuum energy between Casimir plates is very much positive in an absolute sense. The gravitational effect of energy depends on its absolute value. That means the vacuum energy between Casimir plates still produces positive spatial curvature, not the negative curvature required for warp drives. Another popular use for the quantum vacuum is as a medium to push against for propulsionless engine systems like the RF resonant cavity thruster, aka the EM drive.
negative energy.
This notion is particularly silly. The fact is, any acceleration of a real particle involves a transfer of momentum between real particles via virtual particles.
I think the only thing that I would see something as being negative energy would be, could possibly be those, what were those space strings, the super strings and space strings? Those are the only things that I could see as being negative energy, if they are like cracks in the universe.
Virtual particles, and hence the quantum vacuum, mediate all
But
forces.
the only way you would be able to
However,
harness that
it's
is
not
if you,
possible
like,
to transfer momentum from a real particle to the vacuum without
like the
getting
Alaskan
another real
bullworm
particle
from
out the other end.
SpongeBob.
That momentum must be given up by the vacuum to produce real particles again. Those particles would become the propellant.
Oh, you know what? Actually, let's see if they've gotten any more information regarding this. 6 years ago? Dog. Come on, PBS Space Time. There's been more information. Oh. 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 What? Who's this? What's DW? What's DW News? I don't know any of these channels. I don't know. Oh, I do know him. We watched some of his videos earlier. We'll watch this one.
If you are a Marvel movie fan, then you know about Doctor Strange. You know, the rich neurosurgeon whose quest to heal his injured hands after a car crash led him to study esoteric powers. And by being able to use these powers, he became a
Literally
superhero
goals in
of
life.
the Marvel Cinematic Universe.
That's all I
One
want to
of the
be is
keys
Doctor
to Doctor
Strange in
Strange's
life.
amazing powers is the Eye of Agamotto, a mystical amulet made by the sorcerer Agamotto. It houses a glowing green gem called the Time Stone. It gives whoever possesses it the ability to alter and manipulate time. In the movie, Doctor Strange uses it to save Earth from destruction by a demon, Dormammu, by trapping him in an endless time loop. It's thanks to the Time Stone that the stories of the Marvel Universe can follow all kinds of convoluted timelines. This powerful gem is one of the 6 Infinity Stones around which much of the action in the movie franchise revolves. But this is all just far-fetched fantasy, right? Well, yes and no.
Time crystals scare
As
me.
with many Hollywood sci-fi movies,
Whenever they came out
what
with
you see
this,
on
this
screen
kind of freaked me
in
out
the
because
Marvel
I kind of
franchise
started to
might
think,
seem
well,
like
what if our
pure
universe
invention,
is just
but
a
in
time,
fact
one time,
draws on a
we're
surprising
trapped in a
amount of
time
real
crystal.
science,
We're in the
pushed
simulation of
to
a
the
time
limits
crystal.
of plausibility perhaps, but nevertheless based in proper physics. So how is this based on real science? Well, the idea is that the Time Stone is in fact an example of an object that physicists have recently dreamed up and now even made for real. A real time stone?
So if you're watching the video, I'll full screen this just over it real quick.
Object that physicists have recently dreamed up.
So you see how they had the animation like breaking apart and then reforming back together and then breaking apart and then reforming back together. That is basically what a time crystal is. And so right here in this little animation, you can see it almost looks like it's pulsing. You see these dark bands and then you see these white bands and you see them kind of like resonate. They kind of like shift and you can see like the wave kind of in there. Well, that was the energy within that crystal basically releasing the energy, it not having any more energy in the system, and then it creating new energy and re-releasing and then losing that energy. So it was like creating energy at a timed interval, which shouldn't be possible. So it technically created more energy than what was put into it, which breaks one of the laws of physics.
How does this work? That's coming up.
So that's kind of I was thinking, well, maybe our universe is within a time crystal because, you know, there have been theories where the Big Bang, it's a big explosion and then everything contracts back into itself. You know, the universe is expanding and it can only expand to a certain point before there's a big snap. And that's all that energy, you know, we had the big explosion, the energy being released, and then the energy being reformed within itself just to be re-released. So it could be like, you know, a repeating thing, a repeating universe. So that kind of threw me into a spiral, but then I was like, that's kind of crazy that I'm thinking that with no information given to me.
Before we get into time stones and how they work, I'd like to give a big shout out to Magellan TV, today's sponsor. One of the best documentaries I recently watched is on the mysterious disappearance of genius Italian physicist Torre Majorana. In 1938, while traveling by ship from Palermo to Naples, he disappeared and was never found. He may have staged his own disappearance, but he made
the real
huge
Thanos is probably
to
chill.
the understanding of dark matter and the atomic nucleus. You'll find this and thousands of other quality documentaries on Magellan TV. It's a new kind of streaming documentary
I didn't take my allergy
created
medicine
by
last
the
night.
filmmakers themselves. Featured subjects include science, history, travel, and technology. Magellan has a special holiday offer right now. For
What
our
is this
international
ad? I'm gonna
users
get
by clicking
banned
the
on
link in the
Twitch for
description.
playing ads that
As
aren't
magical
mine.
as it sounds, it's actually based on an object that has been exciting many physicists recently, and which has now been created inside a quantum computer. It goes by a name that already sounds straight out of the Marvel Universe, a time crystal. So what is a time crystal? We all
mom.
know about ordinary crystals, like this salt crystal. The atoms in them are all lined up in an orderly pattern, as if each sits on a square of a three-dimensional checkerboard, which scientists call a lattice. If you were the size of the quantum Ant-Man,
Here you
standing
go.
on one
Here
of
you
the
go,
atoms,
Alvin. Here's your
and you
Ant-Man.
move in some direction through space, you'd encounter other identical atoms at regular periodic intervals. The atomic structure of an ordinary crystal repeats again and again in space. It's symmetrical,
great
so that if
animation.
you
I feel like
view
I'm
any
watching the
parts of
actual
it,
movie.
you would see the same repeating pattern throughout. The reason that atoms or molecules form crystals is because this puts the structure in its lowest energy state, which all systems in the universe tend towards. In 2012, the theoretical physicist Frank Wilczek, who won the 2004 Nobel Prize in Physics for his work on the structure of subatomic particles, asked whether it might be possible to make crystals that are symmetrical not in space, but in time. What this means is that the particles it contains are constantly rearranging themselves into different configurations, but at regular intervals in time, they return to exactly the same configuration. It would be a bit like a team of American football players who are moving all around after the snap, but who, every few plays, find themselves back in the same formation.
Reverse,
Wilczek
reverse.
said that behavior like this
Reverse,
would be like the
reverse.
spontaneous emergence of a clock within the system of particles, ticking at a rate it sets for itself. That's why making time crystals isn't just an intellectual exercise for physicists. It could be useful too. They would be natural timekeepers beating to a pulse of their own choosing. Some researchers think that time crystals
Yeah, you could
might
have
help
like an
us make
infinite
better atomic
like
clocks.
clock almost.
Currently, the most accurate timekeepers used, for example, in GPS navigation satellites. Others have suggested that time crystals
Yeah,
made
it's
from
something,
quantum
isn't it?
particles could be components for building
But
quantum
I don't
computers,
watch
which can be much more powerful
sports,
than today's
really.
classical machines. But these applications are speculative
It's
right
sad
now.
to say, but
The regular
American football is
periodic
probably the
behavior
only
that
sport that
Wilczek
I watch.
described looks a lot like a pendulum in a clock, an old grandfather clock. The pendulum swings back and forth,
Tossing the
and
old
at the end of each
pigskin.
to and fro swing, the bob, or all the atoms it contains, returns to the same position. But no ordinary pendulum can swing forever, no matter how well it's made. Friction at the pivot point will make it slowly lose energy until it stops swinging. Wilczek wondered if there was some way of making a collection of quantum
That
particles
animation's kind of
that,
funny.
like a pendulum, will keep moving, but will periodically return to the same positions, and whether they could do this without pumping energy into the system to keep the motion going. His idea got other physicists thinking.
Yeah, well,
Wilczek admitted that a time crystal sounded dangerously like a perpetual motion
technically
machine, which is
it's
forbidden
friction
by the
because
laws of
you can
thermodynamics.
have
But he
gravity
argued that it isn't really
it
because it
acting on an
neither
object
consumes
and it not
nor
reduce
produces
its
energy. However, 3 years later, other physicists
its
proved that actually a quantum
momentum,
time
you know,
crystal
like take an
can't avoid
asteroid
the
traveling
same
through
problem as a
space.
pendulum. It will gradually
There's
dissipate
gravity
the
constantly
energy
acting
it
on
starts
it,
with so
but
that
the force
oscillation
of
will
the
slowly
asteroid
die
is going
away.
too far. Now,
This did
I'm sure
not
maybe over a really,
put an
really
end
long
to
period
the
of time,
story,
you know,
though,
you might be
because
right.
just as you can keep a
Gravity would
pendulum
affect
swinging,
it, so gravity
as long
would
as
have
you
to
give
play a
it little
point
push
in
every so often.
friction.
So too can a time crystal be kept oscillating by feeding
I mean, I
energy
guess yes
into
to
it
both.
with some kind of driving force. This should not be a big deal because we see this happening all the time. For example, in children's playgrounds, as someone can keep a swing going by pushing it. But there happens to be a big difference. When you push a child on a swing, the oscillations happen at the same frequency as the pushing. But physicists realized that for the kind of quantum system that Wilczek had studied, something odd happens when you produce oscillations by such a periodic driving force. The period of the oscillations, that is the length of time it takes for the particles to return to their original configuration, is not the same as the period of the pushing. It can be twice as long, or 3 times as long, or any whole number multiple. It's as if the particles are saying, thanks for the push, but we're going to vibrate at the frequency we choose, not the one you choose. So it turns out that this kind of behavior is genuine time crystal behavior because the periodicity arises from the interactions of the particles within the crystal and not from the pushing. All the pushing does is it stops the time crystal from running out of energy. And because the periodicity is some whole number,
So it's basically
or
a perpetual
discrete
motion.
multiple of the driving period.
No,
they
this
are
one's
called
actually a different one. I was just
discrete.
about to put that one in the chat too. This one's Arvin Ash.
When Einstein first published the special theory of relativity in 1905,
I got
he
you, I
was
got
either
you.
vehemently ridiculed or ignored. People thought it was just
There you
too
go, there you go.
weird and radical to be real. This guy is not even a working scientist. He's just a patent.
Time crystals. The
No problem.
periodicity of time crystals emerging from within the crystal itself, rather than from any external source, was the inspiration for the idea of time manipulation in the Doctor Strange Marvel movies. Now, I want you to understand that no legitimate scientist really thinks we can manipulate time using time crystals. At least nothing like that yet. But there's some logic to the Marvel madness, and it goes like this. The curious thing about time crystals is that they dance to the beat of their own drum. They take in energy from their surroundings, but their periodic ticking rate is their own. So the idea of the science advisors for the movie was that the time stone is a quantum time crystal that somehow seals off a part of space and time and imposes its own internal clock on the flow of time there. So how does this actually affect real events inside that
I don't know
zone?
what that means.
Here the advisors used another highly speculative idea from the forefront of physics called the holographic universe. It roughly says that the total amount of information inside a volume of space can be encoded on the boundary of that volume. Relating this to our universe, it means that all the information contained in our universe, including time, could be encoded on its boundary, infinitely far away. You can imagine this like a 3D hologram created on a 2D surface. Now you might ask, is that what the real world is like? A kind of quantum projection on the boundary of the universe? The problem is no one knows for sure because it's mathematically identical. But this idea of the Marvel
How's that for like
scientists is not
anxiety
as crazy
inducing?
as it might
That we're just a picture. We're just a picture playing on a screen that the universe has decided to play.
out. It has its roots in real science. And that's the idea the Marvel advisors ran with. What it would mean is that all of reality, everything that happens, is basically a kind of quantum computation taking place in that quantum boundary realm. In this picture, you could say that everything, including us, is made of quantum code. So the time stone, being a quantum time crystal, can take a patch of that quantum code, a bit of reality, whether past, present, or future, and rewire it to transform the way time moves within it. The time
Not the
stone, taking
editing.
in energy from its surroundings, imposes its own pulse on the way time flows inside the bit of the universe that it controls. Spiros Miklakis explains it this way. The Eye of Agamotto is a time crystal that can generate its own quantum dynamics despite being driven by the external environment at whatever frequency. Is this confusing and far-fetched? Sure. But it's not all total fantasy because time crystals are real and we've made them by controlling quantum matter. How did we do this? One of the ways to make a quantum time crystal is
Here
to
we
take
go,
a
talking
row of
about the
atoms
spins.
that act a little like magnets. They have a spin, which can point in one direction or the other, up or down. In the
So
time
this right
crystal
here
state,
is all quantum mechanics is. It's all about the spin or the rotation of whatever particle they're looking at. Are you talking about the time crystal in Doctor Strange? Or the time stone? Yeah. I mean, technically, see, I have a hard time understanding the difference between like time as what we think of time, like on a clock, and time as like a physical property. I have a hard time figuring that out. I can't wrap my head around that. And I mean, I guess
the
our
spins
time
would
to
keep
us
flipping
doesn't actually exist.
back
What
and
we
forth
describe as
along
time
the row,
isn't time.
like a stadium wave. They would do this with some kind of period, making the structure a time crystal.
Yeah,
You
it
would
could
need
be.
to keep adding energy in order to sustain this wave, and then also figure out a way to dissipate this energy so that the system does not become too hot and fall apart. In 2017, two teams reported that they had made discrete quantum time crystals experimentally in chains of spins. For example, by suspending a row of charged atoms in an electromagnetic trap. Still though, they couldn't entirely prevent these systems from absorbing too much energy. It wasn't until 2021 that two teams of scientists independently made a discrete quantum time crystal that could in theory keep oscillating forever. They made them actually
Of all people, it was
quantum
Google.
computers. Quantum computers do their calculations using quantum bits, or qubits, which are like particles with spin that can point up or down. And these up or down states encode the ones and zeros of binary information. These bits are manipulated using the rules of quantum mechanics, which allows quantum computers to do things that aren't possible in normal classical computers.
That's a
In
pretty
these
good graphic.
experiments, the oscillations died away after only about 100 cycles. But that's because the quantum bits in any of today's quantum computers become scrambled in just a second or less as they interact with the stuff around them. This is a process called quantum decoherence. But it wasn't due to any failure of the time crystal itself. I made a video on decoherence if you want to learn more about that process. Now the question can be raised, was this a simulation of a time crystal conducted on a quantum computer? Or did they create a real time crystal from the computer's quantum bits? The funny thing is, no one knows for sure, but there may not be any difference. It was a time crystal made from the actual quantum objects that make up the computer's quantum bits. And it works pulsing away for as long as the
That's
computer can
crazy.
keep its bits in
That's
their collective
crazy.
quantum state. So we can now say that
Probably.
quantum time crystals
FBI, open
do
up.
indeed really exist in the world.
Alvin, we
But
need
so
your
far,
soundboard.
the idea of these time crystals being able to create some kind of isolated holographic quantum realm.
Now, I will say, this guy's stuff, it does bring in a lot of like stuff that's not science. So when watching his stuff, just try and keep that in mind. Like he tries to use like real world comparisons that we can relate to easily, which for me work, but I think for some people they could, misunderstand the point that he's trying to make. But oh yeah, absolutely. I think so. I mean, it makes it more interesting. You're engaged. Look at all these nice people in the comments. Yeah, I do like his use of, where was it? Yeah, explanation and visualization of sciences. Yeah, I really like his visualizations because it helps you kind of realize all the different components that are going on, but in one image. Exactly, and that's my problem. I want to make every fiction, well, not every, but I like to live in my imagination. Maybe we should do something on quantum simulations, because I don't know a whole lot about those. I don't want to like learn how to do it. I just want to know like what. Oh, here we go. This one will actually be good because this
The
one.
Nobel Prize in Physics is typically...
This one is actually super cool. Quantum entanglement. Yeah, not Godzilla, and not like. Twilight. Let's not do that. Anything else is fine. No Godzilla, no Twilight. I'm just kidding. I watched Twilight the other day.
awarded to
Quantum
scientists
entanglement
who
is
make
spooky.
sense of nature, those whose discoveries render the universe more comprehensible.
How far away?
But the
are we from
2022
announcement?
Nobel has been awarded to 3 physicists who revealed that the universe is even stranger than we thought. This year's Physics Nobel laureates are John Clauser, Alain Aspect, and Anton Zeilinger, who together are responsible for a series of ingenious experiments that proved that the strangest prediction of quantum mechanics is actually true. It's the prediction that Einstein refused to accept. The idea that two quantum systems can be entangled, bound to each other, such that they can influence each other instantaneously over any distance. This spooky action at a distance, as Einstein called it, is in seeming violation of his own theory of relativity, which tells us that no causal influence can travel faster than light. Clauser and Aspect achieved the rarest of feats. They proved Einstein wrong, while Zeilinger greatly advanced our understanding and practical application of the phenomenon of quantum entanglement. Of course,
And you know what I think has been really, really interesting is that lately they've been making big kind of, maybe not big deals, but I've seen them as big deals um, regarding like NASA announcements and stuff like that. Like they've been doing, I think whenever with their most recent, what was it, a telescope that they launched? You know, they did a pretty big announcement for the images that they received. I mean, granted, they were the best images we've ever received looking into deep space, but like they kind of made it a big deal, which I thought was interesting, because I guess I haven't seen that being done in a long time. So it kind of makes me excited for at least the near future, that we can get back into the whole science mindset. I don't know what I did.
we've talked about quantum entanglement once or twice in the past, but today I want to tell you about a series of brilliant experiments celebrated by this year's Nobel. Let's start with a simple thought experiment. You have two balls, one black, one white. You close your eyes, shuffle the balls, and place each in an identical box. You put the first box in a rocket and send it to the moon, while you keep the second box with you on Earth. While that box is closed, the ball on the moon has a 50-50 chance of being black or white. You open your box and you instantly learn the colour of the ball on the moon. So, did you cause information to travel faster than light? Of course not. The information about the ball's colours was always there with the balls, you just learned which was which. But now imagine that these are quantum balls with entangled quantum colours. According to quantum mechanics, we not only don't know which is which until the box is open, but the colours of the balls are fundamentally undefined. Each ball is in a superposition state of maybe black, maybe white, until a measurement is made. Opening your box causes the observed ball to have to choose a colour state, which then forces the ball on the moon to choose the opposite. Now you really do seem to have an effect that travels faster than light, with the ball on the moon switching from a superposition state to a defined state as soon as you make your observation. These quantum balls could be any particle from subatomic to molecular scale, and the entangled property could be spin, momentum, or any other quantum property. But why do we have to accept this wacky interpretation? Is there any real difference in the result of the experiment if the colour of the balls is defined at the beginning versus when the box is opened? Why even propose this entanglement and superposition stuff? Well, because quantum mechanics, in its standard form, says so. Quantum systems are described by a mathematical object called the wave function,
Here we go,
which
wave
evolves
function
according
again.
to the
It's
Schrödinger
all about
equation.
the wave function.
The joint wave function of two entangled objects only contains information about the correlation between those objects, not about their specific values. They only gain specific values when observed and the wave function collapses. For our quantum balls to know their own colour the whole time, there would need to be extra information not contained in their wave function. There are a few different interpretations of quantum mechanics that allow this hidden information, and they are collectively known as hidden variable theories. Einstein thought that such hidden information must exist, while others, like Niels Bohr, insisted that the wave function was the complete description of a quantum system.
What is this?
In almost every scientific debate, physicists side with Einstein, but not in this case. Quantum mechanics was just too successful, and Niels Bohr was aggressive in pushing his Copenhagen interpretation. It became dogma, while for a while it was career suicide to question the orthodoxy, for example by researching hidden variable theories. David Bohm got the worst of that with his pilot wave theory, which we talk about in another video. John Stuart Bell was another hidden variable heretic. This Irish physicist didn't necessarily believe in them, but he wasn't content to just accept the Copenhagen interpretation without properly testing it. And he also realized that one could reveal the existence of hidden information without actually measuring that information or even testing a specific hidden variables theory. We've talked about these Bell tests previously, if you want to see exactly how this works. In short though,
Yeah,
in
of course we
1964,
do.
Bell came up with his Bell theorem, which shows that there should be a particular statistical correlation between the measured properties of entangled particles if the particles themselves hold the information about their internal states, and a different statistical relationship if those properties
Well,
really
yeah,
are
like
decided information about their
so
themselves
basically, if the
hold
particle themselves hold the information about their internal states, then that particle is technically observing itself. So there would already be
the information about their internal states, and a different
No,
statistical
maybe.
relationship if those properties really are decided at the moment of measurement. In particular, the so-called Bell inequality would be true if there are hidden variables contained in the particles and violated otherwise. Finally, there was a real test that we could use to check for
No.
hidden variables.
I don't think
However,
I was right.
it wasn't until
I
1969
do
that
too,
the
but
first Bell
they're
test was
kind of hard to
performed,
understand.
and
Like, there's
that
a
was
lot
by
of this
one of our
stuff that I'm like, I
2022
don't think I
Nobel laureates,
understand what he's
John
saying.
Clauser. So why
But-
did it take 5 years? Well, Bell tests are really hard to perform. They require the production of entangled states, which have to be manipulated and measured without breaking the exceedingly delicate correlation between the particles. But also, to do a Bell test was to question the status quo, so it was hard to get support for the significant effort required. Clauser talks about the time he proposed his idea for the experiment to Richard Feynman, who promptly kicked him out of his office. Apparently
Get out
Feynman
my
thought it was
office.
pointless because standard quantum mechanics was clearly correct. Clauser and his student Stuart J. Friedman were not to be deterred. They had figured out a brilliant experiment and they were going to try it. It went like this. They blasted a beam of calcium atoms through the intense light of an arc lamp. That light excited electrons in calcium atoms to a higher energy level, and they would then drop down again with the lost energy carried away by photons. One of the possible electron transitions was between two states that had zero quantum spin, and which also resulted in the creation of two photons. Spin is the quantum version of angular momentum. Because the atom's spin hadn't changed in this transition, in order to conserve angular momentum, the pair of photons needed to have a total spin of zero, which translates to them having opposite circular polarizations.
Okay.
Standard quantum mechanics says that those polarizations are undefined until measurement, when they will always turn out to be opposite to each other. Hidden variable theories, on the other hand, allow the polarization to be set at the moment that the photons are created. By measuring those polarizations, by passing both photons through polarizers, Clauser and Friedman could perform a Bell test. Bell inequality was convincingly violated in their experiment, which means quantum mechanics was working exactly as expected, implying no hidden variables,
Okay.
just as Feynman had told them. But the case wasn't quite closed. John Bell himself pointed out that hidden variables would still be a thing, even if the Bell test said otherwise.
Well, yeah.
The result of a quantum measurement depends on how you make the measurement. In the case of this experiment, the orientation of the polarizers determined which polarizations the experiment was sensitive to. Bell's theorem assumed that the choice of measurement is completely free and independent of the particle creation process. But in Clauser's experiment, the polarizers were fixed in position through the whole experiment. Their orientation was already decided when the entangled photons were produced. So what if that orientation had some influence on the polarization direction of the photons at the moment of their creation? Then the photons might carry hidden information about the eventual
Bye,
measurement
red, blue
direction
makes
the whole
white.
time, and
Thank
sort
you
of
for watching the
conspire to
videos
look
and
like
hanging
standard
out. I
quantum
appreciate
mechanics,
it.
even if they had real hidden
If you ever find
variables.
anything interesting,
To
send it to me.
close
I'll take a
this
look at it.
loophole,
Maybe
it
react
would be
to it on
necessary to
stream.
somehow set the measurement direction after
Yeah, we'll
the
definitely meet
photons
in
were
the
produced.
Matrix.
That sounds incredibly difficult because, in case you didn't know, photons move pretty fast. But when you're a brilliant experimentalist, incredibly difficult is your bread and butter, and so we meet our second laureate, Alain Aspect. Aspect's setup was very similar to Clauser's, with a beam of
45
calcium atoms
minutes,
excited
y'all.
by light, this time a laser
Alvin.
rather than an arc lamp. But the main difference was in the polarizers.
I was like, Alvin's been
In
gone
order
for a
to
minute.
change the measurement direction of a
I was
polarizer,
like,
you have to
he
rotate
either
it.
went back to work,
But it's kind of
or-
hard to do that faster than a photon can travel across your optical bench. Aspect found a way to randomize measurement direction without moving the polarizers at all. The trick was to use a type of transducer, in this
Oh,
case
yeah, I
a
would too.
chunk of quartz, that bends the path of light in different ways
I used to have a really
depending
cool
on whether
job,
the quartz is vibrating.
where we had
And that
couches
vibration
and an Xbox
can be turned on
and a
and
nap
off with an
corner,
electrical
and
current.
we also had
That means our entangled
like a full
photons could be sent to
kitchen.
different polarizers
We'd have drinks
depending on an
sometimes.
electrical switch, a switch that could be turned on and off quickly and randomly
That was a fun
in the
job.
tiny intervals between the creation of the photon and their arrival at the transducer. All of this means that the photons can't know how they're going to be measured at
Okay, I need to
in
watch this
different
again
ways.
because this.
Measurement direction
I watched everything
is
else in
your
this video and it started to make
bread
sense,
and
and I still
butter.
don't understand
And so
this
we
part.
meet our second laureate, Alan Aspect. Aspect's setup was very similar to Klaus's, with a beam of calcium atoms excited by light, this time a laser rather than an arc lamp. But the main difference was in the
You know what
polarizers.
time it is.
In order to change the measurement direction of a polarizer, you have to rotate it. But it's kind of hard to do that faster than a photon can travel across your optical bench. Aspect found a way to randomize measurement direction without moving the polarizers at all. The trick was to use a type of transducer, in this case a
Transducer.
chunk of quartz, that bends the path of light in different ways depending on whether the quartz is vibrating. And that vibration can be turned on and off with an electrical current. That means our entangled photons could be sent to different polarizers depending on an electrical switch, a switch that could be turned on and off quickly and randomly in the tiny intervals between the creation of the photon and their arrival at the transducer. All of this means that the photons can't know how they're going to be measured at the moment of their creation, which, if you recall, was a potential loophole in the Klauser and Friedman experiment. The Bell inequalities were also violated in Alan Aspect's experiment, dealing another blow to hidden variable theories. So, did Aspect close the final loophole? Not quite. There are two ways that the Bell inequalities could be violated without quantum entanglement being as spooky as Einstein feared. Well, actually, these ways are still spooky, but in different ways.
Spooky.
Now, the first loophole I already mentioned, what if the choice of measurement is not independent of the creation of the entangled particles? Aspect's experiment seemed to eliminate that possibility by making that choice after the particles were produced. But what if the random number generator controlling the transducer wasn't really random? After all,
this was
signals
actually
could
a
have
different
traveled to
job.
both the calcium atom and the random number generator
I left
from
that
some
job for the
common
one I got laid off
influence,
at.
causing them to conspire to violate Bell's inequalities.
Oops.
This is the idea called superdeterminism, basically stating that the particles are not only correlated with each other, but also with the random number generator or the physicist choosing the measurement direction. So ultimately, the universe has no choice but to always hide the existence of hidden variables. Now, we've discussed superdeterminism before, so you can decide for yourself whether that's a reasonable idea.
I
but
fucking
John
missed,
Bell
dude.
certainly did.
I did it again.
Without
I'm
inequalities.
so sorry, Alvin. You're
switch
gonna have to watch this for
of
a
light.
third time because I'm trying to find
But
where I can look at or watch the new announcements coming out today. YouTube. Okay. Can I put this? Okay, so that goes live in an hour. Damn, are we gonna watch both of these at the same time? We are multitaskers to the max. Let's see. Where's it be at? Meanwhile, sit tight and wait for their live stream here. Okay, perfect. The announcement will be live on YouTube. Okay. Oh shit. Alvin. I'm a dumbass. Hold on. Hold on. You gotta see my face. Alvin. Where's my face? Alvin. It's tomorrow. We're gonna have to do this all over again tomorrow. Or do I just do like a 24-hour stream? Should I just do a 24-hour stream, stay awake, just keep watching these videos for 24 hours, see how much knowledge we can get in the 24 hours before the live stream happens? I mean, I guess it's a good that we got a head start on it. So the announcements for all this stuff that I was looking at doesn't happen until tomorrow. I thought it was today. So I'm stupid. Can't trust me for news. Just don't sleep. You're crazy. I need so much sleep. It's crazy. I sleep like... I went to bed last night at like 11:30. Woke up at like midnight. Went back to sleep at like 12:30. Woke up at like 1. Went to sleep at 2. Woke up at 3:30. Went to sleep at 4. And then finally woke up at 8:30. I was like, geez. Oh yeah, pregame. Totally fine. And honestly, there's not a whole lot of other stuff going on. Like, maybe I'll play Diablo tomorrow before. Because I'm trying to get to level 50. Oh.
Faster than a photon can travel across your optical bench. Aspect found a way to randomize measurement direction without moving the polarizers at all. The trick was to use a type of transducer,
Maybe
in this case a
red
chunk
blue
of
makes
quartz
white will
that
join
bends
us
the path
tomorrow.
of light in different ways depending on whether the quartz is vibrating. And that vibration can be turned on and off with an electrical current. That means our entangled photons could be sent to different polarizers depending on an electrical switch. A switch
Okay.
that could be turned on and off quickly and randomly in the tiny intervals between the creation of the photon and their arrival at the transducer. All of this means that the photons can't know how they're going to be
that's not
measured at
true.
the moment of their creation, which, if you recall,
Oh, well,
was
I
a
guess,
potential
yeah.
loophole
Yeah,
in
yeah.
the Clauser and Friedman experiment. The Bell inequalities were also violated in Alain Aspect's experiment, dealing another blow to hidden variable theories. So, did Aspect close the final loophole? Not quite. There are two ways that the Bell inequalities could be violated without quantum entanglement being as spooky as Einstein feared. Well, actually, these ways are still spooky, but in different ways. Now, the first loophole I already mentioned, what if the choice of measurement is not independent of the creation of the entangled particles? Aspect's experiment seemed to eliminate that possibility by making that choice after the particles were produced. But what if the random number generator controlling the transducer wasn't really random? After all, signals could...
So, I'll explain this experiment if you're watching. So, the calcium ions are right here, and they're being beamed across this laser. And then this laser creates photons, and then the photons are passed through an electric beam. But they did this experiment right here was meant to get rid of the variable of, or I'm sorry, this right here, this variable, so like this space in between here of the photons being created, I believe right here, and then being measured over here was made to reduce the variable of there already being a predetermined path for the photons. So in the previous experiment, I think these two parts, this and this, were combined. So technically, if you ran them together at the same time, the photon would have been generated and would have already had a predetermined path on which polarizer to pass through. So it already had information on the outcome of itself. But this space right here allows for the photon to not know which polarizer it will be passing through. therefore reducing that variable, and I guess it contradicted a previous theory.
Could have traveled to both the calcium atom and the random number generator
Honestly,
from some common
Chloe,
influence, causing them to conspire
love
to
her.
violate
She's so
Bell's
much fun.
inequalities.
I'm level
This
44
is
in
the
Diablo.
idea
I'm trying
called
to get to level 50.
superdeterminism,
Because once you're at
basically
level 50, I
stating
think
that
you
the
can start
particles
doing, like,
are not only
real-world
correlated with
stuff.
each other, but also with the random number generator or the physicist choosing the measurement direction. So ultimately, the universe has no
like
choice
PvP,
but
like
to always
events,
hide the existence of hidden
raids and
variables.
stuff, maybe.
Now, we've discussed superdeterminism before, so you can decide for yourself whether that's a reasonable idea, but John Bell certainly did not think that it was plausible. But even without superdeterminism, there's another loophole. Bell's theorem can be used to rule out the existence of local hidden variables. It can rule out that the secret information about the entangled particle states lives in the particles themselves. That's what local means here. But there could still be hidden variables that exist in the global wave function of the entangled particles. Clauser and Aspect's
Absolutely, like
experiments
interference.
ruled out local hidden variables, but that may mean they ruled out locality rather than hidden information. Any violation of locality still means that some sort of influence travels faster than light. The sort of spookiness that Einstein hated. One way or another, our Nobel laureates have revealed a universe stranger than many are comfortable with. Okay, what about our third laureate, Anton Zeilinger? Clauser and Aspect's work was all about testing the fundamentals of quantum mechanics, about getting closer to what its weirdness is really telling us about the world. But their efforts also led to very practical results. They, and others like them, advanced our ability to create and manipulate entangled quantum states. And Zeilinger put these to good use. He may be the most famous for demonstrating quantum teleportation. This is a phenomenon in which a quantum state is transferred between two particles via an intermediate particle that's entangled
I
with
think
them
that's
both.
probably it. I think
We'll
I'm going to be
save
done
the
with
awesome
these videos
details for another
today.
time. The
We've done
important
a
thing
lot
right
of
now
learning.
is that quantum teleportation
And we still have 7 minutes to go, and I'm not paying attention anymore, so I mean, I'm kind of getting bored of it for right now. I do have the live streams already pulled up on Google Chrome for tomorrow, so I don't have to look for theirs. I think. Yeah. I will keep those pulled up just because I don't want to have to look for those again. What time is it, Alvin? I think I'm going to get off early today. I've done a lot of learning, and my brain's kind of fried. I don't really have anything to do for the rest of the day. I probably need to start some laundry. I'll probably do that. But I think that's probably it. I think I'm going to call it quits today. Let me... Still locked out of my TikTok on my computer, so I can't get into it. What? Why is that still on that screen? I'm not really tired. Surprisingly. And I didn't even have coffee or caffeine today. My face is up. Okay. Yeah, I didn't get any caffeine today. I only had water. I did have some potato chips and like 3 pieces of this clementine because it was jank. It was bad. And then I had some potato chips. Look how shaky my hands are. And then I had some water. But I don't know. Depending on how I'm feeling later, I might stream some Diablo. I might not do my face, but maybe I'll do audio. I don't know. 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 I don't know what I'm gonna do. We'll see. But I hope you have a good day at work. I hope it's not crazy for you. I hope you're feeling rested after your nap. And then I also appreciate Red Blue Makes White for hopping in earlier. I had a good time watching those videos with you. I did not have my brake fluid. Not today. I think I should probably not do that. That doesn't seem healthy. So I'm probably just gonna go to like CVS and get Mio caffeine. They may have some like vitamin Mio or something, but the that just has way too much sugar in it, I feel like. And man, I mean, like yesterday I could not sleep and I didn't even take a nap. So no brake fluid. Probably not today. Maybe not tomorrow. That'll be a long stream thing. Whenever I do like one day maybe I'll do like an 8-hour stream. But I'll have to plan stuff for that because that seems like a really long time. What I need to do is I need to work on getting clips loaded up to TikTok and I need to make a Twitter. That's what I need to do. But I don't want to do that. I don't want to do any of that. None of that. I just want to hang out, stream, talk to you, and whoever else is in chat, and watch videos and play games. But, okay, that'll do it. I'm just stalling now. I'm just stalling. Stalling for views. It's for the content, okay? Don't judge me. What is this fucking music? Is it Hades? Please stop. You're gonna ruin my end stream. It won't close. Help. What is going on? Okay, bye. Bye, Alvin. I'll see you later. I'll talk to you later. Probably today in Discord. Okay, bye.
I bet she's not missing that owl now.